Hello students, in this video I would like to explain chemical properties of haloalkane and haloarenes. Now under that the reactions of haloalkanes are explained first. We know that there are different types of possible reactions, among which one important reaction given by haloalkanes are nucleophilic substitution reaction. So nucleophiles are negatively charged species or electron donors. When reacting with a haloalkane, it is substituting the halogen to form the new substance with the attachment of the nucleophile, such that when an haloalkane is treated with aqueous alkali like NaOH or KOH, OH group substitutes the halogen group so that we can get alcohol. So haloalkane to alcohol can be obtained by substitution reaction with aqueous alkali. Next, the same product can be obtained by hydrolysis, means heating with water, but the previous one gives the better formation of alcohol. Now, next is reaction with alkoxide. Salt of alcohol when reacts with haloalkane, then RO minus, this nucleophile substitutes the halogen, giving rise the ether. So ether is obtained from haloalkane by reaction with alkoxide. Now primary amine can be obtained from haloalkane by reaction with ammonia. Now substituted ammonia, that means 1 degree amine, when reacts with haloalkane we get the 2 degree amine. 2 degree amine when reacts with haloalkane we get the 3 degree amine by the substitution of the halogen. Next is when haloalkane is reacted with KCN. Here it is an ionic compound, so K plus and Cn minus ion is formed. So this K plus and Cn minus, from which Cn minus is the nucleophile, it substitutes the halogen, giving rise the nitrile, the cyanide compound. So here the carbon chain is increasing, means we can use this transformation for the enhancement of carbon in the chain. Now when haloalkane is treated with silver cyanide, now the product here is the isocyanide. Follow here, KCN is ionic, therefore the nucleophilic center is the carbon. But when AgCN, which is being covalent in nature, there is bond between carbon and the silver atom, therefore the electrons on nitrogen atom, that acts as the nucleophile. So nucleophilic center is now nitrogen, and therefore the product is isocyanide, that is linking through this nitrogen is taking place with this CH2 group. So isonitrile, isocyanide is the product. Similarly, when KNO2 is reacted with potassium nitrite is reacted with the haloalkane, we get the nitrite compound. So here, being ionic in nature, NO2 minus, where oxygen is acting as the nucleophilic center. But when it is silver nitrite, nitrogen, the lone pair, being it is being covalent in nature, there is bond between silver and nitrogen, and no free O minus ion is there. Therefore, the nitrogen ion behaving as the nucleophilic center, giving rise the nitro compound. So haloalkane to nitroalkane can be obtained by treatment with silver nitride. Next, reduction of haloalkane can be carried out with lithium aluminum hydride to obtain an alkane. But if we get the higher alkane, then we can react the haloalkane with the metallic alkyl lithium type of metallic alkyl metal compound, organometallic compound. So here we get a new R group, that means the carbon chain is increasing. And again, when haloalkane is reacted with silver salt of carboxylic acid, we get the ester. So in this way, different compounds are obtained from haloalkane by treatment with different reagents. Means we need to follow what is used, what reagent is used to obtain what resulting compound. Now all these reactions are nucleophilic substitution reactions. these nucleophilic substitution reactions can follow two kinds of mechanism. Number one is SN1, stated as substitution nucleophilic unimolecular. In this reaction, what happens? It is a two-step process. Say a 3-degree haloalkane, when treated with a nucleophilic agent like aqueous alkali, we get the alcohol by following the two steps process. In the first step, which is a rate determining step and as well as a slowest step, giving rise the curved cation. This is a 3-degree stable curved cation formed. Now in the second step, the nucleophile attacks this curved cation to give rise the resulting alcohol, which is a first step. Now among these two steps, the first one is slowest one, that is the formation of curved cation, and therefore it is the rate determining step, and hence if we write the rate equation for this SN1 reaction, we can follow the rate is equals to rate constant into concentration of the reactant involved in the first step. So since only one kind of reactant is present, its concentration is involved in the rate determining step. Therefore, in the rate equation, therefore the molecularity of the reaction is 1 and hence it is stated as SN1. Now the reactivity order of the haloalkane for this SN1 reaction is from 1 degree to 2 degree to 3 degree haloalkane. The reactivity increases as because we know that in this reaction there is formation of curved cation intermediate, and since 3 degree curved cation is the most stable, therefore the reactivity for the 3 degree curved cation in SN1 substitution reaction is highest. Now if we follow the stereochemistry of this SN1 reaction, we can follow that here this carbon is a chiral center, so this is an optically active compound, and if we state that this compound in which the groups attached with this carbon, where Br is getting the highest priority and R dash is getting the next highest priority and C is the next one. So we can follow that in this structure, if we move from A to B to C, it is moving in a clockwise direction, and this can be stated as having R nomenclature. And next in the mechanism, this carbon halogen bond is broken to form this curved cation, which is having an sp2 carbon, this carbon is sp2 hybridized, so it is a planar form. This curved cation is in a plane. Now in the next step, when this nucleophile is attacking, it can attack from this side of the plane or from the back side of the plane, giving rise to products. In one, we can follow that here the highest priority group A, then B, then C, we can move in a clockwise direction. So it is having a R nomenclature, it is having R structure. We can follow that it is the same one with the reactant. So here it is retaining its original structure. So retention takes place when this thing is formed, but when this one is formed, when OH group is coming from the back side, we are getting that this is A, this is B, and this is C. So A to B to C, movement from groups to higher priority to lower priority group, gives an anti-clockwise rotation. So this is giving rise an S isomer. So if the probability of formation of these two compounds, as because it is a planar one and there is 50% chance of this attack of the nucleophile from both the sides, therefore the resultant products can also have the priority yield as 50% and 50%. So what will happen? The resulting mixture will be optically inactive. That means it will be a racemic mixture. So in SN1 reaction, starting with an optically active compound, we will be getting a mixture of two optically active compounds. Each one is having 50% product, and their rotation, their specific rotation will also be opposite, and hence the mixture will be optically inactive. So the stereochemistry of SN1 reaction can be stated as racemization takes place in SN1 reaction. Now if we follow the energy profile diagram for this SN1 reaction, this is the energy of the reactant. It is going to the transition state 1, therefrom it is coming to this product. So here it is the carb cation formed. Next, from the carb cation the product is formed. Now we can follow the activation energy for the first step is greater than that of the second step, and therefore the first step for the SN1 reaction is the slower one, and this slower step follows the determines the rate of the overall reaction. So in this graph we can follow that this is an SN1 reactions energy profile diagram where activation energy for the first step is greater than that of the second step. Now if we follow the another mechanism, that is the SN2 mechanism, substitution nucleophilic bimolecular. So here we can follow the reactivity order is the 3 degree is having lowest reactivity, and the reactivity increases towards the 1 degree halide. Now here the reaction follows a single step. Say this is an optically active compound where A is given the priority, Br is given highest priority, then R dash, then R. So it is having a clockwise movement of the groups. If we move from A to B to C, it is clockwise rotation. So it can be stated as, say, it is having an R configuration. Now when the nucleophile is attacking, nucleophile attacks this carbon from the backside of the halide, which is stated as the leaving group, resulting this intermediate. So this bond is going to be formed and this bond is going to be broken, resulting the product. We can follow that since OH minus is coming from the backside of the halide, therefore the resultant compound that is formed, in which the if we follow the priority group, means A is OH is having highest priority, then B R dash, which is B, then R C. So it is from A to B to C given an anti-clockwise rotation, so it is giving rise an S isomer. So what we can follow that in SN2 reaction, inversion of configuration R to S is taking place. If we start with an S compound, it will give rise an R compound for optically active compounds. Now here you can follow that in this reaction, this carbon atom where the nucleophile is going to attack, if there is a small group in these bonds, then there will be lesser steric hindrance and the nucleophile can attack this active center easily, and therefore for 1 degree halide where it may be all are hydrogen, so smaller group nucleophile will be easily attack this active center and the leaving group can leave. Then if the groups here are bigger in size, gradually we move from 1 degree to 2 degree to 3 degree, the size of these groups are increasing due to higher steric hindrance, the reactivity decreases. Therefore we can follow that in this reaction it is a single step process, so the reactant concentrations involved are in their rate equation are this reactant and also the nucleophile concentration. So if we write the rate equation, there two species are present and their concentrations are present. So it is stated as its molecularity, this reaction having molecularity 2, and hence it is a substitution nucleophilic bimolecular reaction. And I have already mentioned the stereochemistry of the reaction is inversion of configuration takes place. Means if we start with an R isomer, it will give rise S. If we start with S, it will give rise R. Now note these 2 points. The rate of SN2 reaction, I have given an example here, from 3 degree towards the 1 degree and then to methyl halide, the rate is increasing, and the rate also depends on the ability of this leaving group, means how easily it leaves from the active center. Now if the size of this group is bigger, then the carbon halogen bond is broken easily. So we can follow that from chloro, bromo to iodo, the reactivity increases as because the size of the halogen group gradually increases and hence the reactivity increases. Here the energy profile diagram for SN2 reaction is also explained. You can follow that. It is a single step process. This is the activation energy, the reactant crossing a transition state going to form a product. So in comparison to the SN1 reaction, which was a two-step process, we can follow in the energy profile diagram. The SN2 reaction follows a single step process. Thank you.